Just hello, good afternoon, everybody. Just bring this people at that bottom. Let me see. So I think I am audible to everyone. Yes. Okay, very good afternoon. Please minimize. Uh, Here myself is Shubhendu Noskor from Department of Chemistry, BIT Mesra. Now, today we have assembled here to start our online sessions. I will start with the first module of the chemistry paper CH101R1. Here, in the first module, you see these are the topics which we need to cover. First of all, the introduction of chemical bonding, then Varna's theory, bonding in coordination complexes, then crystal field theory and different geometries in the crystal field and different geometries, octahedral, tetrahedral, square planar, etc. Then we'll calculate the crystal field stabilization energy and allied with the Jahn-Teller theorem, followed by spectral and electronic and magnetic properties of the coordination complexes. Excuse me. Okay, sorry. So let's start with our first module. First of all, in the introduction of chemical bonding, we can start with a very simple starting a very brief introduction to chemical bonding. Is that we know that how many types of bondings, chemical bondings are maybe available. That means there is first of all it is a ionic bond. Next, number 2 is covalent bond, and number 3 is metallic bond. This part, whatever will be covered here, the whole part will be available in the notes and the question answer module provided to you. So, ionic bond, as we know that there will be the provision of an electropositive and electronegative element so that they can form a ion pairs like A plus and B minus by the transfer of an electron from A to B in their atomic form. So the electrostatic interaction, electrostatic attractive force, that is the reason for the ionic bond, and for the covalent bond, it is basically the mutual sharing of electron by the overlap of the atomic orbitals containing electron each, so that each of them provide one particular one electron to form a two electron bond. And thirdly, the metallic bond, it is little bit different. Where you see in the first case, in the ionic bond, one component was electropositive, another was electronegative. In the second case, in the covalent, both of them are electronegative, as they share their electrons through the orbital overlap. And in the third case, they are basically suppose in the third case, where all the participating atoms are electropositive in nature, and they share their valence electron to form a band type structure to form a metallic bond. So these are the three types of bonding available in a chemical bond. Now, here we are concerned with the coordination complex. So coordination bond is a special type of covalent bond where a particular atom donates a lone pair of electron to the other. They do not share. That is, this A will be giving two electrons to B to form a two-center two-electron bond. Two-center means A, B, two centers, and they are connected by a covalent bond which contains two electrons. So therefore, we will be here. Okay, we will be in this part. In the covalent bond, a special case of coordination bond is a special case of covalent bond where a particular partner provides both the electrons. Now, let's have a very clear idea about the double salts, like molecules like. Okay, so double salts are the aggregates of two different simple salts which produce which aggregates two simple salts. That means that contains two cations and two different types of anions along with lots of other solvent molecules. Suppose the potash alum like this molecule. Now, the characteristics of double salt is that when you dissolve it in water, the individual component ions they exist. That means it will produce potassium ion. There in the solution there will be potassium ion. There will be aluminium 3+. There will be sulfate ions. Okay, along with water. Now, in this context, when we consider the coordination complex, that may contain n number of metals, where n can be from 1 to a huge number for up to the range of polymers. So they have the general electronic. They have the general. In coordination chemistry, the bonds formed are represented by this type of designation, where the L stands for ligand, which donates a pair of electron to metal M. Here, after their formation, they form, suppose, MLN, where n number of L is donated to metal M, forming MLN. Now, the problem with this is that when you dissolve this in water or in any solvent in which it undergoes dissolution, they will not produce the component ions, that is M plus, whatever was M plus or L minus ions, they are not available. Rather, they will give a single component that may be non-ionic also. So this is the basic difference between a double salt and a coordination complex. Now, Okay, so now let's start with the Varna's theory. We will, due to time constraints, we cannot discuss everything in detail, but I will touch all those um, uh, important topics which are important for your exam purpose. Alfred Werner was a Swiss chemist who studied lots of majority of his research work on explaining the bonding in coordination complexes. He framed some, he gives some postulates on the basis of which he got the Nobel Prize in 1913. So the main postulates of Werner's was number one, it could be the metal. But before that, let me represent some standard reference for a coordination complex. Say, if I write the formula MLN, that means they may be of different type depending upon n is equal to 2, 3, 4, 6, etc. So let's suppose it is ML where n is 6. For n is 6, it will be like this.
Some sound is not coming. Some sound is not coming.
Dr. Subhendu, your voice is not coming.
माइक ऑफ कैसे होगा? नहीं शायद उधर से तो फिर ये डॉक्टर सरण ये this voice has been interrupted right now or from the beginning you are not getting my voice?
I asked. It's coming. It's coming.
Coming. Okay.
You can continue.
Mic is off. Mic off. Mic off.
So maybe it is you can automatic
ऑटोमेटिकली मोड पे जाओ। हाँ, ये
setting. Git control with there are only 3 people.
Who's on?
Yeah, you can continue. What is the problem?
Mic is automatically off.
No, right now it is working.
Now it is okay. Yeah.
Okay, so when we am I audible?
Yeah, you are audible.
Okay, so when we are then Alfred Werner proposed few assumptions or his proposal was that the here you see the metals accepts the electrons, lone pair of electrons from the surrounded ligands. So he told that he proposed the first proposal was that metal has metal has
Sir, you're muted again.
Sound is not coming.
चलो स्टार्ट डॉल तक भी नहीं करते थे ऑप्शन क्रॉस करो उसे छोड़ो
लॉगिन में जाओ सबको ऐसा
हाँ
यू लॉगिन में जाओ
Your sound is coming right now.
यस तो क्लियर रेस्ट कर तमरा बहुत दिन छुट्टी है सर प्लीज म्यूट योरसेल्फ
Okay, so is it audible now?
Yeah, it's audible. It's audible.
Okay. So the metal ions have two types of valency, primary valency and secondary valency. Now, primary valency is satisfied by the negatively charged ions, and secondary valency of the metal is satisfied by the neutral or negatively charged molecules or ions. So here, when we see these two types of valency, now suppose here M has +2 charge. If M has 2 plus charge, then and if L has 0 charge, then the overall charge will be 2 plus. Okay, so this is a coordination complex, but this is not a neutral molecule, rather it is an ion. In order to neutralize this, we need certain negatively charged ions which will be placed here. Suppose that is an halide. So as the charge, total charge, overall charge is +2, it requires 2 such halide ions to neutralize the overall charge. Here we will call this X is satisfying the primary valency and these L are satisfied the secondary valency. Okay, so primary valency and secondary valency, it was the main concept of Alfred Werner, which can explain lots of chemical properties which are the results obtained at that time. Moreover, in some cases, suppose if L is negatively charged, if L is negatively charged, then if L is negatively charged, then L can satisfy both So if L is negatively charged, then it can satisfy both the primary and secondary valency simultaneously. Therefore, and the second main second important assumptions was no वो उसमें कुछ दिखता नहीं है वो light color हो जाता है. Second important assumption was that secondary valency has a vectorial property or a directional property in 3 dimension. That means the orientation of the molecules or ions which satisfy the secondary valency, they will be spatially oriented in 3 dimension at a particular direction only. Particular direction means if the total number of L is 4, then it has certain directions which gives rise to either tetrahedral or square planar geometry. For 6, they give rise to certain geometry. For 7, okay, in this way, similarly for 3, 5, etc. So all these secondary valencies has a directional characteristics, which is another main assumption of Werner. Now, once we get the some molecular formula, suppose actually he did synthesize lots of oh,
Last one. This all.
okay, let it be here. Okay, suppose we are we synthesized the molecules like cobalt, NH3, sorry. Is it visible? Sorry, cobalt C.
Dr. Subhendu, your sound is not coming.
Is it visible whatever I have written here?
Yeah, it is visible.
Okay, he reported there are total 5 molecules. In these 5 molecules, they have the molecular formula of cobalt Cl3, 6NH3. In the second one, 5NH3 and 1 water. In the third one, 5NH3, and in the fourth one, 4NH3. But the fourth one, it actually he got 2 different isomers from here, and he named these as in the luteo-cobaltic, luteo, then rosio, then trasio, okay, and parpurio and violio. So these 5 complex he synthesized. the most important chemical identification of these 5 complex was the treatment with silver nitrate. When the molecules are dissolved in water and is treated with excess silver nitrate, then he found that different amount of silver chloride was precipitated. The different amount of silver chloride which was precipitated are like this. Say I am taking a different color here. So for this case, he got, for the first one, he got 3 moles of AgCl. Okay. For the first, he got 3 moles of AgCl. Then for the second, also he got the 3 moles of AgCl. For the third, he got 2 moles of AgCl, and for the fourth, he got 1 moles of AgCl each. Okay, so the values are like this: 3, 3, 2, 1, 1. Now, with the amount of silver chloride formed, he tried to explain the formula of the entity and achieved to the and reached the conclusion that the first molecule is formed with the formula cobalt. Sorry. Cobalt NH3 whole 6 Cl3. Because he got 3 moles of AgCl, that means the ions outside the third bracket, that much amount of AgCl is produced. So he named the entity inside the third bracket as the coordination sphere. So the coordination sphere, outer coordination sphere, whatever anions are present, that much amount of silver chloride is formed. From there, and for the second one, he gave the formula as cobalt NH3 whole 5. There is one more water molecule also, and outside 3 chloride ions. So from the second one, he also got the same equivalent 3 moles of silver chloride. But if I consider the third one, in third one, the formula will be cobalt there, because there are 5 ammonia molecule, NH3 whole 5, and there is no water in this case, so it will include 1 chloride inside the coordination sphere, leaving 2 chloride outside the coordination sphere. So you see, whatever is present at the outside of the coordination sphere, that much amount of silver chloride is formed. So in the fourth case, it will be cobalt NH3 whole 4 Cl2. Outside there is only 1 chlorine, so only 1 silver chloride is formed. From here you see, this is very important for exam purpose. Just try to understand these. Here, in the first molecule, only ammonia is acting as the ligand. In the second molecule, 5 ammonia and 1 water molecule are acting as ligand. In all these cases, in these first 2 cases, all the ligands are neutral in nature. But in the third and fourth case, chloride has ion. There is 1 chloride ion in the third molecule and 2 chloride ions in the fourth molecule. Now we know that chloride ion has a charge uninegative ion. So as it is inside the coordination sphere, it is simultaneously satisfying both the primary valency and the secondary valency. Okay, so cobalt C charge for the fourth molecule is satisfied in this way: 1 chloride which is present outside the first coordination sphere and 2 chloride ions which are present inside the coordination sphere. So this is how the chloride ion is satisfying both the primary and secondary valency. Now from these molecules, if you take them in the solution, instead of they will dissociate into, say, the first one, it will dissociate into cobalt NH3 whole 6 plus 3 plus 3 Cl minus. Okay, but the last one, it will dissociate as cobalt NH3 whole 4 Cl2 Cl2 plus 1 plus 1 Cl minus. So what will be the number of total ions formed from the first molecule? That is 4. The cation is cobalt NH3 whole 6 3 plus, and the anion is 3 chloride ions. For the last molecule, there will be total 2 ions produced, cobalt NH3 whole 4 Cl2 plus, that is the cation, and the anion is Cl minus. So I think you have now you will be able to answer the question that how much amount of silver chloride is formed from any coordination complex. Just first you will have to write the right formula for that complex. Okay, so with this I am closing the Varner's theory here, Varner's coordination theory here. Next, I think I have forgot to add one more slide for ligand. Okay, so for that I am just minimizing it. Okay, and I can also do it here. It is a coming. हम फर्स्ट स्लाइड में ही करेंगे। इधर नहीं होगा। एक्चुअली ये शेयर्ड है इसलिए लग रहा है नहीं हो रहा है। इस पे okay, so now let's try to understand different types of ligands. Ligands are those group of molecules or ions containing lone pair of electrons, which can be donated to the vacant orbitals of metal ion. Now, ligands can be of different type. Depending upon their denticity. Depending upon their denticity means the number of sites by which the ligand can be donated simultaneously to metal ions. So, depending on the basis of denticity, the ligand are classified as monodentate, bidentate, and polydentate. Okay, so monodentate ligands are usually they contains is an atom having the lone pair of electrons. So any common examples like X or amines, so NR3 or phosphines, or you can say these are halides, or neutral like amines, or say water, or say H2S, or there are lots of examples. Okay, So these are the monodentate ligands where there are one donor site which can donate that lone pair of electron. We know water has two lone pairs of electron over oxygen, and that can be donated easily to a metal ion. So these are called monodentate. But the donor atom is only one, oxygen, or say in thiol or sulfides, it is sulfur. In amines, it is nitrogen. In phosphines, it will be phosphorus. Okay, there will be only one donor atom. Similarly, in halides, there are only one donor atom. But when we talk about bidentate ligands, there are more than one donor atom. The best example is definitely they are some group of organic molecules. So the best example is this one, NH2, CH2, CH2, NH2. This is a famous ligand called ethylene diamine and abbreviated as small en. This molecule can donate to a metal ion by two sides, that is say NH2 and NH2, CH2, CH2. So they can form bonds in this way, forming a that's why they are called bidentate. Similarly, you can also go for the tridentate with molecules like the another amines like these. Like this. Say if you take a metal here, it will donate in this way. So from three different donor sites, that's why it is a tridentate ligand. In your lab, you have performed the estimation of total hardness of water, which is basically a complexometric titration. In that titration, we use ethylene diamine tetraacetate ion. That ethylene diamine tetraacetate ion is a hexadentate ligand, and it will come under the category of polydentate ligand. In ethylene diamine tetraacetate ion, ethylene diamine backbone to this CO2H, 4 CO2H. So you see there are 6 different sites, 2 nitrogen and 4 oxygen from carboxylate groups, which can simultaneously form a chelate complex with the metal ion. Okay, a very strong complex and a very high stability constant, because there are 6 5-member chelate rings formed, which gives extra stability to the system. So these are the different types of ligands which are mostly important for in the coordination chemistry. Now I will complete the ligand portion here. If you have any question, then you can post in the chat box. Let's come to an important topic, isomerism in coordination complexes. Isomerism in coordination, as we know that isomers are basically, we consider those as isomers, which is as a definition, the same molecular formula, but different, molecules having same, with the same molecular formula, but they have some difference either in their structure or in their property of optical property. So isomers, which are basically the arrangement of the ligands in different coordination complexes, will be different. Now, in coordination chemistry, there are 2 basic different types of isomers. One is structural isomer, another is stereoisomer. So as you see here, the structural isomer part, what is written here? Compounds with different connections between atoms. Compounds with different connections between atoms. So this is their basic characteristics. Now, there may be several types of which can come under this category. The first one is linkage isomerism. In linkage isomerism means a same ligand will be linking to the metal ion by different atoms. So it is also called an ambidentate ligands, where say a molecules like this one, cobalt NH3 NO2Br. I am first telling the second one because that is the common form. This is the nitro form. Here ligand is connected. Here ligand NO2 is connected to the metal through nitrogen. Okay, through this atom. But if you see the molecule just above this one, here the ligand is connected to the metal through oxygen. So what is the difference? There is no difference in molecular formula. Only difference is in the linkage. Linkage of, in this first case, it is to oxygen. In the second case, it is to nitrogen. And they are giving different isomers. The second case is the ionization isomer. If you see the molecular formula of this written in black, here both of them, the molecular formula is same. It is only the rearrangement of the outer sphere counter anion. Okay, in the first case, the sulfate ion is outside the coordination sphere. In the second case, bromide ion is outside the coordination sphere. But here definitely there is a change in the charge of the in the overall charge. In the overall charge, you see here the overall charge is +2, and here the overall charge is +1. Okay, but in both the case, charge on the metal complex is same, that is 3. Here 3, and here also this is 3. Molecular formula same, but only the exchange of the counter anion that is giving rise to ionization isomer. Polymerization isomer, it is not exactly polymer, but the term was coined at the very beginning. Polymer means large number. Here only the reputation can be made up to nowadays it is available also. Anyway, you see the basic formula is PtCl2NH3(2). Now, if you multiply this by 2, you will get the new molecule PtNH3(4), PtCl4. Here it is different. The second one has both the cation and anion are coordination complex. Okay, so it has the charge of 2+ and it has the charge of 2-. Coordination isomers. Coordination isomers. Here the complex cation and anions are also encountered. The cobalt is available. Ammonia ions are attached with cobalt, and here in the anion, cyanide ions are attached with chromium. But in the second case, they exchange the coordination sphere. The ligands, ammonia and cyanide, they exchange the metal ions. So it is a coordination isomer. Hydration isomer. All the molecules are same with the basic formula of chromium H2O(6Cl). But rearrangement of the water molecules inside the coordination sphere that can be changed, forming 6 molecules of water inside coordination sphere. In the first one, in the second one, there are 5 molecules. In the third one, there are 4 molecules. So in order to fulfill the coordination number, the chloride ions enters gradually. This should be 3. This is wrong. This should be 3. Okay. In the second molecule, one chloride enters inside the coordination sphere. In the third molecule, again another one molecule of chloride ligand enters inside the coordination sphere. And in the same proportion, number of water molecules goes outside the coordination sphere. So this is the hydration isomer. Now you come to the stereoisomer. compounds with the same connectivity but different spatial arrangement. Different spatial arrangement means in three-dimensional they will be their orientation will be different. They are of two types. One is diastereoisomerism and another is enantiomerism. Diastereoisomers are those which gives rise to cis-trans isomer, which are also known as geometric isomers. In the cis-trans isomer, they are of the normal types of cis-trans isomer cis between different in organic chemistry, but in a coordination complex this will be little bit different. Say for the first molecule MA2B2, you will definitely get two different types of isomers MAABB. Okay, and another one MAABB. So the first one is a trans isomer and in the second one is a cis isomer. Okay, for the second type of formula MA2BC, that is also possible. You will get the two isomers. In one case, for both of them, cis and trans, two isomers are available. This will be complicated if we go for the higher number of higher geometries, say octahedral geometry, there will be more number of isomers available. In the case of optical isomers or enantiomers, they are represented in different ways. Their capability, their capacity to rotate the plane polarized light in either direction, either it may be clockwise or anti-clockwise when placed under the in the plane polarized light. So depending on the direction of the rotation, these are classified by different nomenclatures. In some cases, in organic cases, you will get D and L. Okay, but in coordination complexes, they are represented by delta or lambda. Delta or lambda, they are same. Delta is dextrorotatory, lambda is levorotatory, but the way of representation is different. The typical examples for these molecules are of the formula cobalt En whole 3. Cobalt En whole 3 is a molecule like this, say in cobalt. Okay. Now this molecule, this is there are 6 nitrogen atoms. So 6 nitrogen atoms can be attached to the central cobalt by forming the coordination bond. Okay, we can represent it there. We can represent this in this way. Okay, so when we represent it in this way, there are 6 bonds and we are looking through a particular plane, a triangular plane, then it will be like this. Now, if you take a mirror image of this one, suppose you are going to take a mirror image of this one. So it is shown here. It is shown here. It's for this, the mirror image is this one, but they will not superimpose with each other. One cannot be fit over the other, and they have a enantiomeric relationship. So these are the 2 isomers obtained for the molecule cobalt tris-ethylenediamine. Okay, so this is the a very gist representation of the isomerism in coordination complexes. I think you have seen here on the left side, there in exam different types of examples will come. You will be asked to identify which kind of isomerism is possible in these, or you can be directly asked give the example of linkage isomerism or ionization isomerism, or on the right side the example of optical isomerism. Alternatively, the examples will be given. You need to identify the type of isomerism in that. So I think coordination. Okay, so now I can shift to the bonding theories of coordination complexes. There are different theories in coordination complex. Different means whatever are available as a normal theory. There are three theories. Number one is VBT. VBT is valence bond theory. Number two is for the coordination complex. This is CFT, crystal field theory, and number three is MOT or molecular orbital theory. So these three theory, with the help of these three theory, we can explain the bonding in coordination complexes. The very first proposed or the very first approach was the valence bond theory by Hitler and London around it was in 1927. But that was for the simple hydrogen molecule, for the simple H2 plus ion. Rather, it was further developed from time to time. Then come the molecular orbital theory, and for the crystal field theory again come after that. Okay, so in your as per our syllabus, we have the introduction to valence bond theory, but the detail of crystal field theory we have right now we have kept outside the molecular orbital theory. So VBT is the first proposed theory for the coordination complex. Here, according to VBT, the valence bonds are only applicable. So according to valence bond theory, the metal ions are both the metal ions and the ligands, they undergo hybridization. But the hybridization of the ligand is not important, is not considered here. Rather, it is only the metal ion. So metal ions, we know that it is the transition elements which of the with the d orbitals, transition elements, which are particularly important to form the coordination complexes because of the availability of the 5d orbitals, which have large number of orbitals, 5 orbitals, which have vacant orbitals that can accommodate the electrons in them or lone pairs of electrons in them. So prior to form a bond, they undergo hybridization. Different types of hybridizations are possible. Now here we saw with the coordination number, which geometry will be there with the allied hybridization along with the example. This is taken from only from the tutorials which have been provided to you. So you can correlate these things with your tutorials. Suppose coordination number 2, it has a, you see, it is its hybridization is sp and the example is AgNH3 whole 2. Now, how is AgNH3 whole 2? Definitely, you know, say AgNH3 NH3. This is linear. In trigonal, the hybridization is sp2. Trigonal means there are 3 ligands. So AgPr3. So Ag, this. There will be 3 bonds forming a triangle. Now for coordination number 4, there are 2 possibilities, tetrahedral and square planar. In tetrahedral, they undergoes a sp3 types of hybridization. The example is tetraaqueo beryllium 2 plus cation. This sp3 hybridization very simple. It will beryllium there are 1s and 3p orbitals. Those can undergo a hybridization of sp3 and they can accommodate the lone pairs of electrons from order. But in case of permanganate ion, that is that is also tetrahedral. But here the valence shell is different. Here the 3d orbital is the valence shell. So, and there is no electrons also in the d orbital. It is Mn plus 7 state. So it undergoes D3s type of hybridization. Similarly, in square plane, DsP2 type of hybridization with the NiCN4 NiCN4 2 minus nickel in +2 state. Similarly, for trigonal bipyramid, you will get DsP3, or square pyramid, you'll also get DsP3. These are the example. This is the TBP. TBP means it's like this. Okay. Or the square pyramid, vanadium acetyl acetone, that is the square pyramid. So O, V, and acetyl acetonate. So acetyl acetonate is O, like this type of molecule. Square pyramidal. In coordination number 6 ligands. So one example is cobalt Ni3O6. You will always find the 6 donor atoms. Here there are 6 ammonia atoms. Here there are 6 fluoride atoms, 6 fluoride ions. And here this is a diphenyl thiocarbazide, and it is see, there is 3, but there are 2 sulfur in each of them. Okay, the formula is like this. Okay, so this is the formula PH2C2H2. Okay, this will be attached to with these 2 sulfur atoms. This is attaching with molybdenum. So 3 such ligands. So it is completing the coordination sphere with 6 donor atoms, 6 donor sulfur atoms. So these are the examples. This is a summary of geometry, hybridization along with the example. Next, I will discuss 2 or 3 cases here where it will, and from there we can coin the term as inner orbital or outer orbital complex. For the example, if we take the formation of cobalt Ni3O6 3+, it has a cobalt 3+ ion, so it is a D6 electronic configuration. There are 6 electrons, and these are basically 4s, and this is 4d, and 2 more are there, which is not drawn here. That should be considered. Now, what happens? The D2 here the ligand is ammonia. Okay. Here the ligand is ammonia, and D2 is, sorry, this was wrongly written. This should be (4p). So this would be 4p. Therefore, what happens? These 6. Now, forget about this. I am not taking this one. It will go there and it will go there. So we are left with 2d, 4s, and 2d, 1s, and 3p. D2sp3 hybridization. So this D2sp3 hybridization. So for this, what happens? Because ammonia is a strong field ligand, it has the capacity to pair up the unpaired electrons in the 3d orbital. So directly come from here to there. These are the paired up electrons. This is the paired up electrons. Now you find here the D2sp3 hybridization, and 6 vacant orbitals and 6 pair of electrons will come here from the 6 ammonia molecules. Okay, so it is showing the D2sp3 hybridization. But when we go for the cobalt F6 3-, fluoride is the is at the extreme end of the spectrochemical series. We will discuss later. That is, it is the weakest ligand. So it does not have the power to pair up the 3D electrons. That's why it leaves as them as it was initially. So 6 electrons over there in the 3D orbital. So it will utilize outer orbitals S, 4s, 4p, and sp3 d2, sp3 d. This sp3 d2 hybridization will take place. That is up to here. Up to here, they are coming here sp3 d2 hybridization. So this sp3 d2 hybridization, there are 6 vacant orbitals in which the 6 lone pair of electrons from fluoride ions are entering here. Okay, these are the 6 lone pair of electrons from the 6 fluoride ions. So in this way, you see the hybridization is here sp3 d2, but here it was d2 sp3. In the first case, it is the outer orbitals. It is the inner 3D orbitals which are being reorganized. That's why it is called a inner orbital complex. Inner orbital complex or low spin complex. But in the second case, it is the outer orbitals. So this is called the outer orbital or the high spin complex. This is low spin because all of them are paired up. The resultant spin here is 0. But here, this is high spin 1, 2, 3, 4. Corresponding to 4 unpaired electrons, it will show the magnetic moments. Here, the example of NiCl4 2- and NiCN4 2-. NiCl4 2-, chloride is again a weak field ligand and it cannot pair up the lone pair of the electrons in the 3D orbital. So it leaves as sp3 hybridization, giving rise to this one, forming 4 pairs of electrons from 4 chloride ions. But in this case of nickel, say NiCN4 2-, CN4 is a cyanide is a strong enough ligand which can pair up the electrons like this. It will go there, forming this one. So there is one vacancy over there, and this vacancy will now be taken by the rest, forming a up to D2 sp2 up to here. Okay, so DSP2 hybridization, and there are 4 vacant cells where 4 lone pairs of electrons can enter, forming the 4 cyanide groups. So here you see there are no unpaired electrons in the second case. So but here there are 2 unpaired electrons. So it is a high spin complex and it is a low spin complex. So with this, I think today we can finish it up here so that in the next class tomorrow we can continue.
If anyone has a questions, they can post their questions. If anyone would like to have their own question, they can post in the team as well. I had given the link also in the chat box. Any questions we have, then please post, or if anything they can ask also.
If you have any doubt, please post your question in the chat box. We will check it and answer. They can also post the question in the team, you know, so. So, okay, so I think right now you cannot raise your questions. Anyway, think it. You can ask me tomorrow also. Okay, so if you do not have, because we do not find any questions over there, so I'm concluding it here. We'll again meet tomorrow at 5. Okay, thank you all. Thank you very much.